would mean that everything below 50 miles would be melted. However, seismic data from thousands of earthquakes show conclusively that the mantle rock is solid down to about 1,800 miles. Karl's law and Jaeger reveal that while the distribution of radioactive elements in Earth is unknown, the radioactivity must be very shallow, not deep, and confined to Earth's thin granite crust. This means the radioactivity is concentrated in the primarily granitic continental materials. So the answer to this first question, Earth's radioactivity is not uniformly distributed throughout Earth, as is expected if Earth evolved. Instead, we see that radioactive elements are concentrated in Earth's granite continental crust. The hydroplate theory will explain why. We now must answer a second question in order to see how heavy elements were created. What conditions or forces could overcome the Coulomb force? Two possibilities exist. They are the Z-pinch and shock collapse. Returning to the bolt of lightning, let's discuss what it is. Atmospheric lightning is a plasma. A plasma occurs upon electrical breakdown of any substance. In this case, the air molecules, mostly nitrogen and oxygen, have been transformed from their normal gaseous state to plasma. This happens as the electrical potential, or voltage, between the clouds and the ground increases above air's dielectric strength. The result is a massive flow of electrons, a current that arcs between the clouds and the ground. After a lightning strike, showers of gamma rays and a burst of neutrons are detected, a result of nuclear reactions and radioactive elements produced by the lightning. So what is happening within the plasma? When electrical current travels through close, parallel wires, a very powerful pinching force is generated known as a Z-pinch. Lightning struck this tube, causing it to be radially compressed or pinched together. The higher the voltage and the closer the wires, the stronger the pinch. In lightning, at electrical breakdown of air, the plasma produced as electrons are stripped from air's nitrogen and oxygen molecules act like closely spaced wires carrying a tremendous flow or current of electrons. So the stripped electrons follow paths that resemble the flow of electrons in closely spaced wires, but the spacing is at a minuscule atomic scale. Remember, the closer the spacing of the wires, the stronger the pinching force. Since the atom's outer electrons are stripped away, positively charged nuclei, rather than flying apart, are powerfully pinched together. The pinch is so strong that it overcomes the Coulomb force, and the strong nuclear force snaps the nuclei together, forming heavy, unstable, radioactive nuclei with short half-lives between 10 and 100 minutes. Of course, all this occurs in an instant, producing the light that we see as a bolt, and intense heat that expands the surrounding air, producing a sonic crack of thunder. This effect is similar to the research that Germany's Dr. Fritz Bosch has demonstrated. An intense electrical field will strip electrons from the surrounding heavy nuclei. Atoms become unstable and throw themselves apart, sometimes changing their decay half-life a billionfold. The term Z-pinch is used because those first studying this phenomena were using the familiar XYZ Cartesian coordinate system in their analysis, and the compressive pinching force was occurring about the Z-axis. Had they set up the force along a different axis, we might be talking about the X or the Y pinch. This is not science fiction or theory. Researchers at Sandia National Laboratories have built this Z-pinch machine and are taking advantage of this powerful force to produce nuclear fusion in an effort to produce a controlled nuclear fusion reactor. Nuclear power plants today are fission reactors. If successful, a fusion reactor would be able to produce great amounts of cheap, clean electrical energy. The Ukraine's Electrodynamics Proton 21 laboratory has also been revealing the tremendous power of the electrical Z-pinch. While stars can only produce the first 26 or so elements, researchers are finding that a focused Z-pinch can produce the entire periodic table of elements and far beyond. Researchers at this laboratory using the Z-pinch can squeeze together a target of pure common nuclei like gold, silver, or lead into previously unknown super heavy elements, many twice as heavy as uranium or lead. These super heavy elements, because they are so large, are unstable and quickly decay back into the more stable 94 natural elements. The process involves passing a beam of electrons traveling near the speed of light into a target electrode of extremely pure metal to produce a focused Z-pinch, which implodes the target's nuclei into a tiny point. Because the point is so small, temperatures in the hot dot reach a staggering 630 million degrees Fahrenheit. The imploding nuclei within the hot dot merge into unstable super-heavy nuclei. The dot then explodes, producing a flash of light, gamma rays, X-rays, and many nuclei fragments of all sizes that repack into the more stable 94 or so, quote, naturally occurring elements and isotopes, plus some super-heavy elements that last for several months before decaying. Incidentally, the stable elements that are produced and are heavier than 60 nucleons end up absorbing the excess heat. Thus, the hydroplate theory solves the problem that has perplexed others. How could the Earth have withstood the heat released by so much accelerated decay? The answer is the heat was absorbed in fusing heavy elements such as uranium. This has been demonstrated in the Proton 21 laboratory. Dr. Adabenko calls it cold packing. So far, 22 different metals have been used for electrodes. All produce similar results. After subjection to the Z-pinch, a portion of the pure material is transformed into lesser amounts of all the naturally occurring elements. Why does this happen? Why do these super heavy elements decay and fragment into the 94 naturally occurring, relatively stable elements, including heavy, slightly unstable radioactive elements that are concentrated in Earth's primarily granite continents? To understand, we need to see what drives instability. Here we see the periodic table with elements color-coded according to their instability. As has been discussed, the larger the nucleus, the greater its potential instability. But this instability is not only due to size, but also to the ratio of the atom's protons to neutrons. For most light elements that are stable, this ratio of protons to neutrons is high at around 1, close to 50% protons, 50% neutrons. For very heavy elements to remain somewhat stable, this proton-to-neutron ratio drops to around 0.67, or roughly 40% protons to 60% neutrons. Remember this difference between these two groups of elements. Now consider what happens when a Z-pinch of many small light nuclei produces a large super-heavy nucleus. Since the large nucleus has been made up of merged, lighter nuclei whose proton-to-neutron ratios are 50-50, the new super-heavy nucleus will retain the same 50-50 ratio, and therefore it is extremely unstable. When all the elements and their many isotopes are plotted according to their proton-to-neutron ratios, and then given an instability rating, the pictured chart is produced. What we see is that if you have too many protons or too many neutrons, the nucleus is extremely unstable, shown here as 100% unstable, and will immediately break up or decay. Stable elements that we are familiar with are located down in what is termed the valley of stability. Notice that the valley curves to the right between points A and C. The 50-50 proton-to-neutron ratio line is shown between points A and B. Viewed from directly above, we can now see the bottom of the valley of stability. We see that uranium-238 is somewhat stable with a half-life of 4.5 billion years, and it plots on one of the sidewalls of the valley. Uranium-238 eventually decays into lead-206, which is stable at the very bottom of the valley. One of the decay products, while uranium-238 decays toward lead-206, is polonium-218. It is very unstable, and we see that it plots along the high rim of the neutron-heavy plateau of instability. Polonium-218 has a half-life of only 3 minutes. Here is the 50-50 ratio line again. Remember, lighter elements have proton-to-neutron ratios near the 50-50 line. If Z-pinched together, these light elements form heavier elements with the same 50-50 ratio. They lie high on the proton-heavy side of the plateau of instability and quickly fission into many smaller fragments, some of which are still radioactive and unstable, like uranium, polonium, etc. We now can see why many question the validity of assuming that uranium-238 to lead-206 and all other parent-daughter decay ratios represent the age of a rock sample. If powerful electrical currents that were once a consequence of a global flood produced radioactive elements, then many mysteries of Earth's radioactivity are explained. Radiometric dates are meaningless. For evolutionary theory, the alleged mountain of data in support of great uniformitarian epochs of time really adds up to nothing more than a very precise set of ratios, not dates. But how does hydroplate theory tie Earth's radioactivity to a recent global flood? The key to seeing how Earth's radioactivity is concentrated in Earth's continental crust is to recognize that the main rock found is granite.